Okay, so a couple things. One, I really was trying, and I'm this close to having a second assignment graded to turn back today, but I'm just not there yet. I'm super close. So they should be done. For certain, you're going to get them back Thursday, and if I finish them before then, I'll put them up on Canvas sooner. And so that's going to change a couple things. Well, I guess that's going to change one thing. Your rewrites for assignment 2. See how sure I was that I was going to have the assignment 2 ready to hand back today, that I even put the rewrite date in under my notes. So I got a little too sure of myself there. So I'm going to change this to Thursday the 20th. If you were going to turn in a rewrite for assignment 1, that's due today, you can hand it to me like hard copy, or you can upload it to Canvas, and you could just use the same submission link for assignment 1, like the same link. It'll let you re-upload more files. And then we're working on assignment 3, is that right?
Yes.
Okay, and that's due on Thursday. And then today, at the end of class, when we're done new material, I'm going to hand out the take-home test. That's due a week from Thursday. And I'm going to hand out the practice in-class test. I have the wrong pile out. I'm going to hand out the practice in-class test, which is in here somewhere, which is right here.
And the practice in-class test is going to have the proofs or whatever that we have.
Yes. Yep. The practice in-class test is not anything that you're going to turn in for a grade. In fact, I will be posting the practice in-class test and my written out solutions to them. So you can use that as a resource. It should give you a decent idea of what to expect when you come to take that test next Thursday. So we're finishing chapter 3 today. We may or may not take the whole time. And then the next 2 classes are going to be like working days. Like this Thursday, you might use it to kind of either start the take-home test or continue working on assignment 3 that's due that day. And then Tuesday, the 18th, is another working day. We're not going to cover any more we're not going to start a new chapter until we get back from break. Does anybody have questions they would like to ask before we continue chapter 3?
What are the questions of the assignment to the board?
Assignment 3 is, were you in class last time? Oh, I think I handed it out, didn't I?
Yeah.
I handed out assignment 3. I do have a couple extras though.
Is it also available online on Canvas?
Oh, it should be online. You know what? That's a good question.
Let's see.
Maybe it is online and maybe I didn't post it. Let's see. I didn't post it. I handed it out though. Did you get a hard copy or no?
No.
Okay. So that's on my to-do list. Post assignment 3. Okay. Other questions? Okay. So we were talking about storing numbers in a computer. We did some binary arithmetic, which is kind of fun. You know, how we do. So, you know, a computer will store a value like and use some certain number of bits, right? So as the number 99 as a base 10 number, if we express that in binary, let's just do a real quick conversion here. Divide by 2, list the remainder, 49 with a remainder of 1, right? Divide by 2, we get 24 with a remainder of 1. Divide by 2, we get 12 with a remainder of 0. Divide by 2, we get 6 with a remainder of 0. Divide by 2, we get 3 with a remainder of 0. Divide by 2, we get 1 with a remainder of 1. Divide by 2, we get 0 with a remainder of 1. How do we use this to figure out what the number is in binary?
The bits at the bottom.
Yeah, so read from the bottom up. So 99 as a base 10 number is 11000011 as a base 2 number. So that's 3, 4, 5, 6, 7 bits. So if we wanted to use 8 bits, we just added a leading 0. And if I wanted to store it using 16 bits, we just add 8 more zeros. Exciting. Now what we're going to do is, so last class, one of the things we did was some arithmetic, right? We did these two addition problems by hand. Not terribly exciting, but what I want us to do is sort of think about how we went through this to construct adders. We're going to first construct the half adder and then the full adder. So the way that we take two digits and decide to add them, right, is we take this digit and this digit, we add them, and then we decide if we have to carry out a digit or not, right? So these added up to 1, and that's just 0, 1, so there's nothing to carry. These guys added up to 2, so that's, I have to drop down a 2 and then carry a 1. And what we want to realize is that when we construct that half adder, there's two outputs that we need to keep track of. What the sum digit is that we write down here, and then what the carry digit is, if there is one. Or not if there is one, but whether or not the carry digit is 0 or 1, okay? So that's what we're going to do here. So the two digits that we line up to add, I'm calling those x and y. And then the two outputs, I'm calling the carry digit c and the sum digit s. And we're going to construct a little table. And it's basically a truth table, and it works the same way that a truth table does. So the inputs, so notice I've got two inputs, right, for those two digits that we're going to add. And I've got 4 rows, because that's going to account for all the possible combinations, the 0, 1 combinations. So they could both be 0. We could have 0, 1. We could have 1, 0. We could have 1, 1. And when we add 0 and 0, the sum is 0, and we carry a 0. When we add 0 and 1, the sum is 1, and we carry a 0. Likewise, for the next one, when we add 1 and 0, the sum is 1, and we carry a 0. And then last, when we add 1 and 1, that's 2, which means we drop down a 0 and carry a 1. Now, because I've written these, oh, okay, my microphone is muted. Hold on. Sorry, Sam, is that better? Hopefully. So it should be all set now. So we're just talking about how we, if these are like the two digits that we line up that we're going to add, like when we're doing the addition, and then like this is the sum digit and this is the carry digit. And we're just sort of trying to emulate what we did like when we added numbers. So each row in that truth table is like looking at a particular column. And then this is the sum digit, and then this up here is the carry digit. Now, because when I made this little truth table, because I put the carry digit first column and then the sum digit last, really when you add them, all I do is write the sum in binary in that order, right? So, and that gives me the desired result. So what we want to do is just figure out, we have two inputs and two outputs, and we're going to construct a little circuit for each of these. One of the things that we're going to need, or we're going to find useful, at least, is to construct a new gate or to use a new gate, and it's the exclusive OR gate for Boolean circuits, or the XOR gate, and it looks kind of like the OR gate, only with a little extra curved line on the back end. And this is the one that produces a 1 if precisely one of the two inputs is 1. You have a 1 and a 0, and then that will produce a 1, and it produces a 0 in the other cases. When we write the Boolean expression, not in a circuit form, we use a little circle plus to denote the XOR operation. So we're going to write the Boolean expressions for these the Boolean expressions, for those two outputs. So when I'm looking for a Boolean expression, I'm starting with a little truth table. I really kind of focus on, where do I get a 1, right? What are the conditions that get me a 1? And then I just write the expression for that. So if I'm focusing on maybe the output for the carry digit, here's the only row where I have a 1. What has to be the case in order to get a 1? They're both 1. Like x is 1 and y is 1. So the carry digit is x times y. The only way that you get a 1 is if they're both 1. And that's the and, or the times. What are the conditions, if we scroll back up here, looking at the table? If I want the expression for the sum digit, here are the rows that give a 1 in the sum column. What are the conditions that make that happen? What's that? X or y, like the OR operation, but not both. It has to be the exclusive OR, because OR always means or both unless we specify otherwise. So we want to make sure we're clear about this, that this is the XOR operation. And that's the circle plus. And we can make a little circuit for this. We got 2 inputs, we got 2 outputs. So here's my input for x. I've got my x input, my y input, and I'm just going to make both. It's almost like having, I'm going to draw a single circuit that produces 2 different independent outputs. So the carry digit is x times y. So I'm going to pass these through an AND gate, and that's the carry digit. And then we're just going to reuse these inputs to construct the sum gate, the sum output. So that's the XOR. I need to pass x and y through an XOR gate. Here's what an XOR gate looks like. Exciting?
Yeah.
Yeah, good. The half adder is kind of incomplete. It doesn't really do the whole job for us, because I'm going to scroll back up to a few examples ago, one of the problems we did Tuesday. If I only allow myself to consider the 2 digits we're adding, in the original numbers, right, that we're adding together, I'm going to miss a scenario like this, right? So like, what if I had to carry a 1 from the previous column, and then when I'm actually adding them, I need to have 3 inputs. So I need to have that carry in digit. So I'm going to make a distinction now between what we carry out and what we carry in. So a carry in is going to be whatever the carry out was from the previous one is our carry in digit in the next column. So we're going to construct now the full adder. So so we have a truth table. Now we have 3 inputs. Notice there are 8 rows, just like we would see with other truth tables. So I'm going to start with my x and y, right? So 0, 0, 0, 1, 1, 0, 1, 1. So I could have those inputs where my carry in is 0. And then I'm just going to repeat these for when my carry in is 1. So 0, 0, 0, 1, 1, 0, 1, 1. And now I'm just going to add these three values together. And again, because my carry out digit column is written first, really all I'm going to do is add these numbers and write the sum as I would write them in binary, because I've ordered the columns in that convenient way. So if I add three zeros together, we just get 0, 0. The next two, the sum is 1, so that's 0, 1, 0, 1. What do we get in the next row? Say that again. 1, 0. Yep. The next 0, 1. Mm-hmm. 1, 0. 1, 0. 1, 1, because that adds up to 3. Great. Now, we're gonna get Boolean expressions for the carry out and the sum digits. We're gonna focus on the carry out first, just because might as well. And just like we did before, the way I'm gonna get this expression is figure out, where do I get a 1? What are the conditions that produce a 1 in the carry out? So that's this row, this row, this row, and this row. I'm going to erase these marks when we begin focusing on the sum output, but this will be helpful for now. And we're going to start with an expression that's not really simplified at all. And we're going to use what we call disjunctive normal form. It's going to give you this expression that looks kind of ugly, but the form itself is easy to get, so it gets us something to start with. So the carry out. So I just note that, so if I look at this first row that I highlighted, carry in is 0, which means I don't have carry in. The x and the y are both 1. So I've got like the carry in not, right, because I don't have that. I do have x, I do have y. So that top highlighted row is going to look like carry in not times x times y, because these are ands, right? All three. The carry in is out, and the x is on, and the y is on, right? All three of those, and that's why I'm using multiplication here. So carry out could be a 1 by being in this row, or it could be a 1 by being in this row. And I'm emphasizing the use of the word or, because what's the operation I'm going to put right here after this term? Plus, because it's an or, right? So plus, now this second row here, or the second highlighted row, what would be the expression, the term I'm going to have for that row?
Cn times x naught times y.
Cn times x naught times y. Yeah, good, right? The x naught is off, the Cn and the y are both on. So I could be in the top row, I could be in that row, or plus, what's the next row?
Cn times x times y naught.
Good. That's why not. Or, what's the last row?
Cn times x times y.
Cn times x times y. Great. So this is what we call disjunctive normal form, or DNF for short. That absolutely is an expression that represents the carry-out digit. But if I thought about drawing a circuit for that expression, already I don't know, it makes me stress out thinking about it, because how many gates? Let's count the operations, right? So carry in, so that this negation is a gate, every times is a gate, every plus is a gate, every not is a gate. So if we count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 gates. That's kind of awful, and I don't want to do it. So I'm not gonna. But what we're going to do is use what we know about Boolean algebra to simplify this expression. And maybe we'll get an expression that's a little bit easier to draw a gate for. And then we'll focus on, once we get that simplified expression, we'll go back and focus on the sum expression. So I'm going to just here, I could probably have put this on the same page, but I'm going to just recreate or copy over what we have, what we just came up with, and then we will and then we'll simplify. Okay, so the first thing I'm going to do is use the fact that addition is commutative, and I'm going to keep the first term where it is, Cn naught xy plus, and then the last term is going to go next, Cn xy. And then I'm going to have the next two terms in their order, so Cn x naught y plus Cn xy. All I did here was I took like this term on the end and threw it, made it second. So far, so good? Okay. So I did that for a reason. I did that because in the first two terms, I'm going to just look at the first two terms as a group. There's a common factor of xy. We could use the distributive property. And in the second two terms, the carry in is a common factor. So the first two terms I'm going to write as x, y, and then carry in naught plus carry in plus, and then in the next one, carry in times x naught y plus, this last one right here on the middle row, that should be carry in xy naught. Sorry about that. So this is getting a little better. I just counted. I think there's 11 gates there, which is certainly better than 15, but I think we can do even better than that. What can we do right here? What is that equal to?
Well, that's an or, which means it's equal to everything, because it's counting both everything that's not and C and everything that is.
Right, so it's so in Boolean algebra, we call that
Yeah,
our 1. Yep. So xy times 1 plus, and now let's focus on this part here in this parentheses. So the conditions that make, the stuff that's highlighted in blue there, the conditions that make that 1 means either x is off and y is on, or x is on and y is off. So I've got one or the other, but not both. How do we write that?
XOR?
That's XOR, yeah. So I've got the carry in and then x XOR y. And so xy times 1 is just xy, and I think that's the last thing to do. So I got xy plus carry in times x XOR y. And this is, I think, the most simplified we can make it. I think it's worth noting that in order to make it as simplified as it can get, we just introduced a new gate. I mean, the XOR gate isn't an independent gate, right? It's constructed to help us save some operations by combining nots and ands and ors together. But this requires, let's see, 1, 2, 3, 4 gates. So that's not too bad. Okay. Ready for the next one? We did the carry out, now we need to do the sum. So I'm going to scroll back up first so we can kind of construct the DNF form for the sum. And then I'll copy it over on the next page. I'm going to erase these highlights because I want to make new ones. Okay, so to make the expression for the sum, I want to focus on the rows where the sum is a 1. So that's that, and that, and that, and that. Okay, who wants to start us off? What's the expression for the top row?
Cn naught times x naught times y.
Mm-hmm. Next.
Plus Cn naught x times y
X
times x times y naught.
times Y naught, yep. Next.
Cn times x times x naught times y.
Mm-hmm. And last.
Cn times x times y.
Mm-hmm. Great. So there's the DNF form, very unsimplified, lots of gates. Don't want to draw it. Let's get a simplified expression. Let's use our Boolean algebra properties to simplify this, and then we'll start working on the circuit. Okay. So again, I'm just going to copy this part over. So I got my Cn naught x naught y plus Cn naught x y naught plus Cn x naught y naught plus Cn x y. Okay. So I'm going to group these. I'm going to look at these grouped again. And I think they're already written in the order I would like to see them in. So if I look at like this first pair, the first two, I've got a carry-in naught that's common to both of those. We could take that out. And then inside, we get x naught y plus x y naught. And then in the next pair, we've got the carry-in that's common to both of them. So I could take that out, and what's left inside?
X, y plus x naught y naught.
Mm-hmm.
Why did the first carry in not?
Oh, it is a knot. Yep, thank you. Good catch. Okay, so now let's focus on this part, the expression in the first set of parentheses here. How could we simplify that? That's the exclusive OR that we saw above. So this is x, XOR y, and then we have carry in. Okay, now this next one, whoops, is not obvious, but I want us to think about this. So with the XOR, we were able to, we think of the XOR as I have precisely one. One of them has to be on and one of them has to be off. And another way to think of that is they have to be different from each other, right? Whatever value X takes on, Y has to take on the other value. They have to be different. Here, they're either both off or they're both on. They're either both zeros or they're both ones. Another way of thinking of that is that they have to take on the same value. Okay.
One.
It's not one, but if we look at, here the rows highlighted in blue, that was our XOR gate, right? Those are the rows that make where they have to take on different values. So if I think of the possible values for X and Y, for them to take on, right? That's what gives us these 4 rows. That's how we start out a truth table. Here's my XOR in the middle, the blue. The other 2 rows that are left, is the ones where they're either both off or they're both on. So what does that make it? What's that? Well, I mean, they're either both zeros or they're both ones. But what I'm trying to get at is the XOR gates are these 2 middle rows. If I just negate that by saying I want the ones that are not those rows, That's what gives us what we're looking for, both off or both on. In other words, it's the complement of the XOR. Yep. Oops, here we are. So this is X XOR Y complement. Does that make sense? Okay. Now already this is looking better because I've got 1, 2, 3, 4, 5, 6, 7 gates. We could make it even better. Okay? So now let's look at the whole thing, right? This whole line that we have. I either have CN off and the XOR on, or CN is on and the XOR is off.
I mean, it's one big XOR gate.
That's like one big XOR gate. I'm going to take the carry in and XOR it with the X XOR Y. And that is 2 gates. So great. Okay, now we're going to make a circuit that's going to have 3 inputs now, the carry in, X and Y, and 2 outputs like we did before, the sum and the carry out. Both of them, you'll note that both of them involve an X XOR Y. So I'm going to, when I make the circuit, I'm going to have to definitely need an XOR gate with X and Y coming into it, but I can use that output twice for each of these two, the sum and the carry out. So let's begin. We have our carry in, we have the X, we have the Y. I know I'm going to need an X XOR Y. So I'm just going to make that here. And if you like, you can even make little notes about what's coming out of each gate, just to kind of keep track. So let's say if we want to do the carry out digit first, I need to pass that XOR in through an AND gate with the carry in. So let's do that first. So this is carry in and then X XOR Y. And I'm going to scroll back up again just to look at what else I need. And I got to pass that through an OR gate where the other input is X and Y. So I got to pass X and Y through an AND gate, and then that output's going to go through an OR gate with what we just produced here. So here's X and Y. And then that's going to go through an OR gate and there's our carry out. Four gates. Great. There's our carry out, and then we need to make the sum digit. So we said that we could reuse this output from the X XOR Y, and then we're going to pass that through an XOR gate with the carry in digit. So let's see. Sometimes things still get a little messy, but that works, right? So there's the carry in, and then the X XOR Y, and these are going through an XOR gate. How's that? Not too bad? Okay. That's the end of chapter 3, I think, right?
Yep.
Okay, so here's what we're doing. I'm going to, because I didn't post it before, I guess, I'm going to post assignment 3 so it's up there, but everybody should have a hard copy if you weren't in class last time, or maybe you just didn't get a hard copy. I've got those to hand out here, and it'll be posted up on Canvas. And then I'm going to hand out the take-home test and the practice in-class test, and I will also, if they're not already up, post those to Canvas right now. They'll be up in just a few minutes. And then you could take time, you could spend time working on assignment 3, or, you know, taking a crack at the practice test or looking over the take-home test. What I would like you to do, I'm going to hand this out. I'm going to hand out the take-home test first, okay? And then what I would like you to do is read the instructions. Don't read the problems yet. I really just want you to take like a few minutes to read the instructions, to understand the academic integrity rules, what you're allowed to do, what you're not allowed to do, and then sign and date that statement at the top. And then once you've done that, feel free to use this time however you wish. I'm going to stop recording.